In this video, we'll go through a bit of an implementation and some examples of how we actually use StereoVision and do the calculations for it. So firstly, we want to work out what our center point for our image is, because we measure our pixels in the X direction based on that center point value and work out how far off it's from our center point value, because we align our cameras between the center points of each of our cameras. And so that's something that we can easily calculate based on the dimensions of the images that are being taken by our camera. We can then, for example, use some rulers and some objects within our environment to do our computation of our intrinsic parameters. We move something a certain depth away from the camera, and based on that, we compute how big it appears in terms of pixels and how big it appears in real life of how many millimeters that particular object is. And that allows us to generate our scale factors, for example. Here we have an example of how we can compute our SX scale factors based on a key object that's 300 millimeters away from us, and looking at the size of that object in terms of how many pixels it represents on the screen and how many pixels or how many millimeters it is in real life. Then what we can do is, using that scale factor and calculating the scale factor for each camera. If it's the same camera, it should have approximately the same scale factor. We can identify a point that we can see in both our images, calculate the distance of that point from our center point for each image. So we get our XL value and our XR value. In this case, it's one of the corners of our Rubik's Cube. We calculate our disparity based on that. And then we can use our equation, Z equals B SX on D, to work out our depth in our image. And here we've calculated our depth to be 301.8 millimeters. The actual depth was 300 millimeters, which is really pretty close. So StereoVision does yield some interesting results for us. Our depth becomes inversely proportional to our disparity. So if we have a larger disparity, a larger difference between our two images, we have a smaller depth, because we're actually closer to those cameras and we can see these things from a larger variance between those two different cameras. And if the things that we're trying to measure distance are a long way away from our cameras, we'll have a very small disparity, which will allow us to compute our depth with less accuracy. Our depth is also proportional to baseline. And so if we want to calculate for objects that are longer away, we'll need to adjust our baseline of our camera to be further apart. However, if we then try and take an image of something that's quite close, we might not be able to see that image or match that image correctly between our two different cameras if the baseline's too large. So there we have a few different ways we can improve our images: increasing our baseline, increasing our focal length, and also decreasing our pixel size. In other words, getting a better camera with a higher resolution. I've mentioned previously, when we're talking about photogrammetry, we want our flat images, images where we have as little lens distortion as possible. Now, this isn't always the case. And so there's various things we can do. A common one is using a checkerboard here, where that checkerboard's seen between both of the cameras, and we can reproject images and remove lens distortion to some degree. One of these processes we call is rectification, where if we've got cameras that have an angle with respect to each other, we can rectify them so they're essentially coplanar with each other. And this requires us essentially to reproject our images as if, rather than being taken like this, it will make them look as if they were taken like this. Now above, there's some disparity maps computed using two different techniques: the sum of square difference technique and zero mean normal cross correlation technique. And you can see that some of these disparity maps perform better than others. Let's move on then to some matching problems. Just like in photogrammetry, occlusions are a problem with StereoVision. Sometimes there's something that we can see from one camera that we can't see from the other camera, like the wheel in this picture here. And sometimes there's not much we can do about this. Likewise, if we've got pictures where we've got featureless regions, we won't have lots of features to actually match between our images. So we'd expect a poor quality of matching between these. If we've got different light levels between our images, or maybe a reflection or a bright spot on one image that's reflected into one camera but not the other camera, it can cause false matches or poor matching between our different images as well. So once we've done our matching algorithm, we want to match a whole lot of points, as many points as we can between the images. Now we might only get 50% matching between those images, which is only half the image really, but based on our occlusions and our bright spots and all of those different things, we're not expecting these to be perfect. And then what we do is for each of these pixel pairs that we've matched, we compute the depth of these pixel pairs and work out what we call a depth map. And our depth map might look something like this. And so we can see things that are in darker blues are further away from us, and things that move towards the reds are closer to us. We can also take more of a photogrammic approach and do our 3D reconstruction and put textures over these and create a 3D texture of a room.